entire file here, and so what topics did it not cover? Let's see. Yeah, definition, even and odd. So you have to understand these definitions here. You have to know how to understand them and how to apply them correctly. So, okay, so even and odd. Okay, let me make some comments about that. So let me say new share. How about this? Okay, here let me make some comments about this, even and odd. But this is not just mentioning about even and odd, but I want you to generally understand these definitions. You have to learn how, you have to learn how to read these definitions and exactly know what they mean. Okay, so and then function f is odd if f of minus x is equal to f of minus f of x for all x. No, maybe I'll number them. Let me call that number 1. This one number 2. Okay, there we go. Okay, so that's the definition of even odd. So now here I want you to make it clear. Number 1, function f is even if f of minus x is equal to f of x for all x, not for some x, but for all x. So here let me say, how about if I give you a question like this? So what kind of question could I give you? I can give you a question like this. Example now, f of x. Let's say f of x. How about let g of x is equal to x squared. Let's say let's say x squared. How about x squared? So we get x squared. Show that function g is even. So how do you show this? How do you show this? Now let me do, let's say, solution 2. Here we have solution 1. Okay, solution. Okay. How about this? Okay, so show that function g is what? Is even. So how do you show that this function g is even? So let me put a bar here in the middle. Okay, so how do you do this? How about this? How about g of 2 is equal to what? 4. G of negative 2 is equal to 4. And this is also equal to our g of 2. And then g of negative 1 is equal to what? Is equal to 1, which is equal to g of 1. And therefore, g is even. Do you think this is correct? Do you think this is the correct argument? Correct argument here?
Yes.
That's the correct argument? So let me ask you this. So let me give you another question. Example. If h of minus x, if h of minus 1 is equal to h of 1, and h of minus 2 is equal to h of 2, is function h even? What do you think?
No.
If h of negative 1 is equal to h of 1 and h of negative 2 is equal to h of 2, The question is function h even means that what I mean by this is must function h be even? That's what I'm saying. Of course, h can be even, but is h always even? That's the question. In other words, function h with above conditions must h be even? That's the question. Must.
Yes.
Should it be even, or is it possible that h is not even? In other words, must h be even? Not is a function, of course, could be even, but in that case, is it necessarily that the function h must be even? Or is it still possible that h is not even? That's the question. So now we basically have these kind of questions here. Okay, so now we come to the bottom here. Again, this is a question to everybody. If h of -1 is equal to h of 1 and h of -2 is equal to h of 2, can we conclude? The question is, let me put an arrow here. Can we conclude that h is even? I guess that's the question. H even or no?
Yes.
H of -1 is equal to h of 1 and h of -2 is equal to h of 2, so then h is even. But let's look at the definition. What does the definition say? The definition says that what? The definition says if h is even, if h of minus x equals f of minus x equals f of x for all x, not for some x. This is the key. So if h of so how do you know? So do you think if h of -1 is equal to h of 1 and h of -2 is equal to h of 3, do you think we can conclude this? Is h of 3 -3 equal to h of 3? And is h of -5 equal to, if h of -5 equal to h of 5? Do you think they're all true?
No.
If h of -1 is equal to h of 1 and h of -2 is equal to h of 2, then do you think h of -3 is also equal to h of 3 and h of -5 is also equal to -5? And then also, how about, let's say, is h of -88 equal to h of what? 88? Do you think all of these are true? Now, in order for this h to be even, all of them must be true. And then dot, not just these, but for all x. The key point here is to understand this is x right here. It has to be true for all x, not some x. So now, if h of -1 is equal to h of -2, if this is true and that is true, is h even? What do you think? Now, all of these true? No. This one is a big no. In fact, this was not just a big no. This one is an angry no. No. Is this a correct argument? If g of -2 is equal, that is equal to g of 2, yeah, that is right. If g of x squared, g of x equals x squared, g of -2 is equal to 4, and that is equal to g of 2. So g of -2 is equal to g of 2, yes, that is true. G of -1 is equal to 1, which is equal to g of 1, no, that is true. But now, therefore, g is even. Is that the correct argument? Is that the correct argument? And the answer is no. Now, this function g is actually an even function. But did you prove it? Did you show? No. Proof is not good. Not good enough. Proof is not enough. Because you have to must show that g of g of negative x is equal to g of negative x is equal to g of x for all of x. See? So in this argument, did we show that g of -x is equal to g of x for all x? Wait 1 second, what happened here? Oops, what happened here? Okay, I'm trying to bring this to a correct place. Okay, there we go. The proof is not enough. Why? Must show that g of minus x equals g of x for all x. What did it show? We only showed that the g of minus x equals g of x only when x equals 1 and 2. 2 and 1, that's all we did. We did not show that g of minus x equals to g of x for all x. Therefore, if you give me a proof like this, that is, if you give me a proof like this, basically a proof like this right here. Again, once again, if you give me a proof like this, then this will be an incorrect argument. The correct argument? No. Therefore, you are not going to get any credit. Not correct. This is incorrect. Incorrect argument? Proof is incorrect. It's not enough. I should say it's insufficient. Okay, so now then g of x, what is the proof then? What is the correct proof? This is what you do. The proof is this. The proof is g of minus x. What is g of minus x? So g of minus x is equal to, what is g of minus x? Well, g of minus x is equal to minus x and then what? Square. So we get this. And this comes out to be x squared, which comes out to be g of x. So let me now write the powers here. So basically we get this. Negative x squared. Because g of x is x squared, g of minus x is equal to minus x squared. And what is minus x squared? That's x squared. And then what is x squared? X squared is g of x. So now we have shown that g of minus x is indeed g of x. And this x could be anything. And therefore, g of what? G of minus x is actually equal to EF. And we can write this as for all. Actually, this is for all x. You only have to write because x can be any letter here. And now this is the correct argument. So this is the proof. Now let me ask you this. Now let me say this. On the other, I can also give you a question like this. Example. This is what a constructing function. A problem on constructing functions. Constructing functions. And this kind of problem is very common too. So what is a problem with constructing functions? It's basically this. The problem kind of looks like this. Find a function f such that, and then blah, 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 blah. Not find points this time, not finding points, but finding functions. And such and such and such. And then what do we have here? And here we have some kind of a criteria. This kind of a problem is very common as well. Very common problem. So let me now give you a question here. So example. Find one function f such that, no need to find all of them, just find one such that f of minus 1 is equal to f of 1 and let me write and here, let me stress this, not or, and f of minus 2 is equal to f of what? 2 and f is not an even function. Write such a function. Write such a function. Write such a function. And verify all conditions. So in this case, what you have to do is two things. Here I gave you a problem. The question is to find such a function. And so you have to first write such a function f, and then you have to verify that the function satisfies all those conditions. What are the conditions which I mentioned right here? The condition is that The condition is that, the condition is this, of course, f of negative 1 is equal to 1. That must be true. And then, of course, that must be this. So this must be true. And then this must be true. And then f should not be a new function. So can you come up with such a function? This is the kind of question I can give you on the test, by the way. Now, how many such functions are there? How many functions are there which satisfy those conditions? There are billions of such functions. Just find one such function. That's all you need. Here, on this case, I'm not asking you to find all such functions. There are zillions of functions out there. Zillion meaning it's a very large number, okay? So, okay, millions of functions. So just find one function. That's all I'm asking. So what function would satisfy that? Well, let me give you a solution. Solution? How about this? F of x is equal to f of x is equal to what? F of x is x minus 1 times x plus 1, and then times x minus 2, and then times x plus 2. And how about x plus 10? So let f of x is equal to x minus 1 times x plus 1 times x minus 2 times x plus 2, and then times x plus 10. Will this function satisfy all those conditions? Do you think will this function satisfy all those conditions? Let's check. So solution is let f be that. So now let's check the conditions. Let's check the conditions here. Check condition. Okay, so let's check the conditions here first. What is f of negative 1? F of negative 1 is 0, which is also equal to f of 1, and they're both 0. So the first condition is met. Is f of negative 1 equal to f of 1? Yes. F of negative 1 is equal to f of 1 because they're both 0. F of negative 1 is 0, f of 1 is 0. So the condition f of negative 1 is equal to f of 1, that is satisfied. Now let's check the next condition. The next condition would be the second condition here. How about f of negative 2 also equal to f of 2 is equal to 0? Yeah. The second condition is also true. Is f of negative 2 equal to 0? Yeah, f of negative 2 equal to 0. Because we see the factor x plus 2 there. So if you plug in x equals negative 2 right here, if you plug in x equals negative 2, then we do find negative 2, then we do find that the 0. So f of negative 2 is 0. F of 2 is also 0 because we have this guy. When you plug in 2, you get a 0. So f of negative 2 is 0, f of 2 is 0, f of negative 2 is equal to f of 2, they're both 0. So that's good. Now, how do you show that this is not a even function? Not a even function? Okay, that's easy way to check too. What is f of 10? What is f of negative 10? Now check the next condition. Check last condition. What is, let's see, what is f of, now I'm coming to the bottom here. What is f of negative 10? What is f of negative 10? Is equal to 0. But, what is f of 10? F of 10 is equal to, plug in here. If you plug in 10, what do you get? We get 9. 9 times 11, and then times, plug in 10, we get 8 times what? 8 times, what is this here? 10, we get 12, and then times 20. And all we care is that this is not 0.
Professor Lee?
This f of negative, let me. Yeah.
What if you created a function such that f of -1, f of 1, f of -2, and f of 2 are not on the graph? Like the points don't exist, would they still be equal?
You know what? Sorry, I'm not understanding your question. What is your question again?
So if I wrote a function like the square root of x minus 3.
Oh yeah, I see. You're saying that it's not defined. If one side is defined and the other side is not defined, then that's not an. If first of all, in order to be an even function, both sides must be defined. For values which are defined, they must be both defined on both sides. So what that means is if f of 3 is defined, then f of -3 should also be defined. If f of 3 is defined, but f of -3 is not defined, then it cannot be an even function or an odd function. So it must be defined. But if f of 3 is not defined and f of -3 is also not defined, that's okay. But for the values where it is defined, they must both sides be defined.
All right, thank you.
Oh, does that make sense? Yeah. So they must be defined and equal. So here is an example. Now this is one of the zeros of functions out there. So we have this. So f of -1 is equal to f of 1 is 0. They're both 0. The first condition met. Second condition met. And note that now f of -10 is 0. But f of -10 is 0 because we see that -10 there at the end, x plus 10. So when you plug in x plus -10, the whole thing becomes 0. So f of -10 is 0. And we know that f of 10 is not 0. So you don't really have to write the whole thing here. All of these things right here, you don't really need it. All we need to know is that this guy is not 0. So in this case, what is this here? So you have this, and then we have all this here. This guy, you don't even have to write. You just have to write that this f of 10 is not 0. And so f of 10 and f of -10 are not the same. That's all we have to show. But f of -1 is still equal to f of 1, and f of -2 is equal to f of 2. Let me now give you another example, another function. How about an easier, maybe easier one? How about this? How about that? How about this here in this solution? How about this? Another solution, another function, another function. There's so many functions out there. Another function is this. How about let f of x? F of x is equal to x minus 1, and then times x plus 1. Very similar. And then times x minus 2, and then times x, and then plus 2. And then, you know what? Just put a square here. Okay, then now what? Then now in this case, what is going to be true? Well, let's see. In this case, f of -1 is equal to f of 1 is equal to 0. And then what is f of -2 is equal to f of 2, which is also equal to 0. Easy to check. And what is f of 3? What is f of f of -3? F of -3. You know what? This is hard to check. Yeah, f of 3. This one is a little bit hard to check. This one, what is f of -3? -3 is going to be you know what? This one negative. Okay, so this is you can check this -3, then -4 times -1. -4 times -3 is -2, and then times this one -3 there, so -5, and then times the -3, so we have -1 squared, so that's a 1, so that's 1. And if you multiply all this, what do you get? You get what is this here? This is going to be minus 8 times 5 minus 40. Now this was a little bit more work, but now what is f of 3? F of 3 is going to be multiplying 3, so we have 2 times what? So this is going to be 2 times, and then 2 times, and then what is this? 3 here, and so that's 4, and then times 3, so we get 1, and then times what? 3, so we get 5 squared, 5 squared, and then squared. When you get that, when you plug that in, in this case, this is positive. So we know that it cannot be equal, obviously, because this is positive, right? So you can just say that this is positive if you like. And that will do, because the f of -3 is a negative number, so and f of 2 is positive, that means they're not equal. But if you want to be more complete, okay, more clean, then yes, I can actually continue this. And what is this here? This 5 squared is 25, 21, this is actually 200. And 200, this is not equal to f of negative 3. Not equal. So here I have given you 2 examples. But how many functions are there? How many functions are there which satisfy all these conditions? There's zeros out there. And then, by the way, on the test, I could ask you to find not one function, but I can ask you to find 3 functions. But now here the trick is this. You should not just write any such function, but you must write a function which is easy to verify. Because I said, write such a function and verify all the conditions. So if you write an ugly function, it will be hard to verify. So the trick is, you find function, any function, which satisfies all the conditions, and it should be easy to verify. Is that fair? So I think this is the kind of problem which I'm more inclined to give you. It's more interesting. And these are functions of type where we have to find the function. A constructing function type problems. Any questions here? So know how to prove and how to prove and how to argue. Again, when you say g of minus 2 is equal to g of 2 and g of minus 1 is equal to g of 1, does that conclude that g is an even function? Can you conclude from here that g is an even function? Therefore, g is a function. Now, note that in this case, g, the function g, is an even function. Yeah, we know that. But the question is, did this argument prove that g is an even function? And the answer is no. The argument is not enough. The argument did not prove that g is an even function. This is the whole point. Yes, g is an even function. Yes, it is. But the proof is not proved. The fact that g is an even function is not proven. It's not proven. Do you get the logic here? Because students come to me, well, that the g is minus equal to g of 2 and g is minus equal to g of 1, so therefore g is a function. Isn't g an even function? Yeah, well, g is an even function. But once again, this argument itself does not logically conclude that g is an even function. So the proof is not good. Proof is not enough. Not enough. You have to show that g of minus x equal to g of x for all x. Everybody, do you understand the argument here? The question is not whether g is an even function or not. We know that g is a function. G is. But here, you have to prove that fact. And if you argue like this, that's not good enough proof. It's not. Because if a function has the same value at negative 1 and 1, and the function has the same value at negative 2 and 2, does that make that function even? No, it doesn't. It doesn't do that. Get that? So you have to be very, very careful with the argument. You're not just stating a fact. You have to show it. You have to show it. I mean, g of x, whether you can prove or not, we know that g of x is an even function. The question is, you must prove it. You have to show. Just saying that g of x is an even function just doesn't do. Here, you have to show it. And this is how we show it. So let me now save this page and then clear this. And now let me go back to our, page. Okay, so now share screen. Let me go back to this. Okay, now we are back to this. Okay, so example, Example 9. Right after example 9, there's the definition even or not. And now example 10, there are 3 functions here. So how do you show that whether these functions are even or odd? Now function f, do you think that's even or odd? Example 10, this guy, f, function f. Do you think that is even or odd?
Even?
That's an even function. And you should be able to prove that. Now function g, is that even or odd? Do you think? What do you think? Well, I can even give you a trig function. Do all of you love trig functions? Should I give you trig functions on tomorrow's test? On tomorrow's test? All of you, you like trigonometry, don't you? Yes or no?
Love it.
No.
All of you, do you love trigonometry?
No.
No, I'm just kidding.
It's my passion.
Your passion. Okay, then that means I should give you some trigonometry then. How about this? Maybe I can give you the HK. How about function? Function, let's say function K, or function K of X. I can say K of X is equal to, and then I can say this. What is function K? Function K is equal to this right here, is equal to sine X, sine of X, and then over what, X cubed, or X cubed, and then plus X.
Never mind, it's not my passion, never mind.
Not your, well, if you don't like it, that means I need to put it, right? My job as a teacher is to put all the things which you all hate, right? Is that true? So if I give a function like this, K of X equal to sine X over X cubed plus X, is that an even function, or is that an odd function, or neither? Can a function be neither even or odd? Yes. Most functions out there are actually not even, they're not odd. They're not even and not odd. So this function here, yes, it is this is an even function, by the way. You can show that. Don't worry. You know what? No tricks on what? On tomorrow's midterm what? Midterm 0.
Thank you.
So anyway.
Thank you.
You don't like tricks, don't you? Okay, all right. Okay, you know what? At this time on midterm 0, I'm not going to give you any tricks. But who knows? If any of you make me mad, then on midterm 1, I will give you a trick, okay? Anyway, no tricks. No tricks. A trick with a T-R-I-G-S. No tricks, okay? Not tricks, but tricks, okay? But no tricks on, anyway, no tricks. All right, I will control myself not to give you any tricks. Yeah. Any questions?
Yes, I have a question. On the function, you're asking on example 10 if a function can be even or odd. If I recall, there are also times where they can be neither. Am I correct?
Yeah, that's right. In fact, most functions are not even and they're not odd. Most functions. In fact, the function h at the end, the last
that's like
one,
that's neither, right?
Even and that is odd.
Okay, thank you.
Now, how do you show that they're not odd? They're not even or not odd. Well, you have to, maybe I'll show you, okay? And then, can a function be even and odd at the same time? Do you think a function can be even and odd at the same time?
No.
Can a function be even and odd at the same time? Actually, the answer is yes. There is one function which is even and odd at the same time. And I'll talk more about that, okay? There's one function. A function can be even and odd at the same time. But there's only one function, which is not so interesting, which is extremely boring. But there is one function out there. And I'll talk a little bit, okay? So what I'm going to do is let me erase all this, and I'm going to show you how to do this. How about h? Let me do h here. So what I'll do is I'll do h. So in this case, let's look at h. Okay, how do you do this? H of minus x. So whether you want to show a function even or odd, we want to we want to evaluate that function at negative x. Why? Because if you okay, let me do this first. Okay, so let me do this first. So because if you look at the definition here, function even if f of minus x is equal to f of x for all x, and f is odd if f of minus x is equal to minus f of x. And note that in both cases we have f of minus x. So either way, we have to evaluate this. So to check a function even or odd, all you have to do is evaluate f of minus x. So we evaluate h of minus x. So h of minus x is equal to replace x for minus x, we get minus x cubed, and then this is equal to phi, and then times minus x squared. So what is that? That will be minus x cubed, and then what? and then plus 5x squared. So we get this 5x squared. Now the question is this equal to f of x? This is equal to h of x? Is it equal to h of x? No. No. And then now the question is then, this is equal to minus h of x? Is that equal to minus h of x? What is h of x? H of x is x cubed plus 5x squared. So is that minus x cubed plus 5x squared? Is that minus h of x? No. So therefore, h is neither, what? H is what? A function h. Function h. F of h is neither what? Even nor odd. Do we still use the word nor? Anyway, I'll just say it this way. It's not odd, not even.
We do still say nor.
Okay, neither even nor odd. So this function h is not even, not odd. It's not. Most of the functions are not even and they're not odd, by the way. Because that is not exactly h of x. Because h of minus x and h of x must be the same for all x values. That means they better be the identical expression. And x cubed plus 5x squared and minus x cubed plus 5a, they are not identical expressions. That means that for some value of x, there will be different values. And therefore, it's not the same function. And then, is that minus h of x? No, that is not exactly minus h of x either. So that is not true either. So therefore, h is not even, not odd. In this case, by the way, for function g, is function g even? Function g also happens to be even. You know, I did not give you any odd function here. Should I give an example? Well, anyway, there's no even function here, but you know, when you see one, you can see it. Okay. Anyway, this is how we check. Let me give an even function then, or how about let me check. How about k of x equal to I can say, right? This is what? This is how about 4 times x, and then plus what? Sine of you know what? Let me just give you a trick function here. I don't have to give you, but you know this. And then if I give you, you know what? Let me not give you a trick here. Maybe okay. So let me just avoid the trick example. Because if I give you sine of x, then you have to know what sine of minus x is, and I don't know. Maybe many of you already forgot that. Okay. So let me do that again. Let me just give you a non-trick example. How about let k of x equal to what? 6 times 6. How about let's say 8x to the subpart, and then minus how about 7? About 2x, and then I'll also give you a very simple example. How about if I put the example 7, and this is 5th power. So this would be a very simple example. K of x equals 8 times x to the 7th power, and the minus 2 times x to the 5th power, and that is an odd function. Okay? So here I didn't give you any odd function, so just give you, there are many odd functions out there, but anyway, that's just one. And you should be able to show that too, all right? Now, you know what, before I do this, maybe before I continue, we have a little bit of time. How about if I do this? Let me save this, and then clear all this. And what I like to do is go and then open up another file. Let me open up a file called Symmetry. Where is my file called Symmetry? Oh, there you go. You know, there's a file called 0206. 0206, Symmetry, odd and even. There you go. This is also one of the files which is actually covered. Okay? 0206. And this is actually a very interesting this is only one-page document, but this page is very condensed. Okay, so we have all this. Now, you don't have to know all the parts here, so definition and all that, and then I have all these here. And some parts you may not understand, so I'm not going to cover that, okay? So anyway, the part which you have to really know is actually this right here. Example, if you look at right above example 5, there's a definition. Definition number 1. A function f is even function if f of minus x equals f of x for every x. In this case, the graph of y plus fx has y-axis symmetry. And then number 2, a function f of x is an odd function if f of minus x equals minus fx for all x. In this case, the graph of y plus f of x has origin symmetry. Okay? Anyway, if you know what that is. Okay, but anyway, when you get to graphing later on, we will go over all that, okay? So maybe, should I go to decimals.com and show you some graphs? Maybe I will show you some examples, okay? So when I get to the web, graphing website. So let me just write a note here. I would like to maybe show you some. How about example 5? Is it even? Yeah, this guy's actually even. And you have to show that that is even. And example 6 is actually odd. You can show that that is odd. Example 7 is not even, not odd. This one is not even, not odd. By the way, most functions are not even, not odd. Okay, so now let's look at after example 7. These are the questions you have to know, and it's kind of interesting. It's kind of important. Okay, so now let's look at this. Example 8 is example 8 star. Find all functions which are both even and odd at the same time, basically. My question to you is this: can a function be even and odd at the same time? And the answer is yes. There is a function. And the function happens to be the zero function. But you have to derive it. Okay. Must here, the question here is this: derive, find or derive the function. There are functions with such conditions. That is, which must be even and odd. That's the condition. Okay, but anyway, I'm not going to do this. Maybe I'll ask you to do that. But let me just show you. So you prove this. Okay, how about you find? Okay, you do this. You do the problem. You find. Okay. But here, let me just get the answer. Give you the answer. The final answer is this. The answer is yes. Answer, yes. F of x is equal to 0. This is the zero function. This is the only function out there which is even and odd at the same time. And that is actually very important. It is an important fact that the function, the zero function, which means f of x equals 0, that is f of x equals 0 for all x, that function is even function and at the same time an odd function. And by the way, this is the only function. This is the only function which is even and odd at the same time. Simultaneously. Now, most functions out there, they are not even, they're not odd. So we might say, oh, you know what? If there are only a few functions out there which are even and odd, and most functions are not even, not odd, why even bother? But there's a reason why this is now the theorem example, which shows up after example 7, example 8, it now shows why the odd and even functions are important. And this also, it will come into play when in calculus. So if you look at the theorem example 8, now here is an important theorem. I don't know whether you have seen the theorem or not, but this theorem has 4 parts. Now, you know what? Let me make a comment about this. Note, you know what? Let's look at example 7. Example 7 is x cubed plus 5x squared. Is this function even or odd? Oh, the typo here. This should be separate. This should be written to the right. But anyway, fx plus x cubed plus 5x squared. Is this even or odd? Is fx plus x cubed plus 5x squared, is that even or odd? Can you tell me? F of x is equal to x cubed plus 5x squared. Is this function even or odd?
Odd.
This guy's odd?
Even.
No, this guy's not even, not odd, by the way. Not even and not odd. This guy's neither. You can show that easily. You can show the f of x. And you know what? It's not when you simplify f of negative x, that will not equal to f of x, and that will not equal to minus of f of x. You can show easily that this one you can show. Okay, can show. Nothing is automatic here. You have to show. You should be able to show all of these things. You can show. Okay, now what we know is this. Even though this function is not an even function, not an odd function, note that this function right here, if you look at this part right here, x cubed, oh, that's actually an odd function. That's an odd function. And then what is this guy here? This guy's actually an even function. And this function f right here happens to be a sum of two functions. One is even and one is odd. So this is kind of interesting. A function which is not even or odd, but this function is actually a sum of two functions, which is an odd and which is a function which is a sum of an even function and an odd function. It's a sum of two functions where one is odd and one is even. So the question is this common? And the theorem, which shows up below example 8, that's exactly what we're going to talk about. Now let's look at theorem 8. Theorem 8 is this. Let f be any function. F be any function. If you have f is any function, then now show that this function right here, this guy is an even function. Sometimes I call this e of x. This one, I can call this guy e of x. And that's an even function. And then now if you honor a function like this, and that's an odd function, you can show that that's an odd function. So you have to show that that's an odd function. Now, number 3 is the kind of conclusion. Note that f of x is actually equal to e of x plus O of x. It turns out that every function out there, even though virtually 99.99% of the functions out there are not even and not odd, what is true is any function out there where most functions are not even and not odd, but every function is a sum of an even and an odd function. It turns out that is always true. Always true. Every function, any function, happens to be an odd function plus an even function. An even function is an odd function. So even function, odd function. Now, and number 4 is more special. Even function f of x, e of x, and O of x are a unique. There's only one way to break it up. So there's only one way to write an odd function and plus an even function. And for example 7, this is it. Odd function is x cubed and plus even function is 5x squared. And there's no other way to break this up in a different way. So, you know what I'm saying? This is odd and this is even. And that's the only way to separate them as even and odd. There's no other way to break it up. So this is the interesting one. And now for calculus students, we're not there yet. So you know what, this one here, we will be getting to this. And we will get into a concept of what we call a derivative. This is the derivative here, and this will show up in, I think, an example. What is this? Chapter 3. We'll get there. And when it gets there, we will see this something like this. And right now, it's meaningless. We did not go over any of these topics here, but it will show up. Okay? So anyway, but you know what? Right now, in pre-calculus, this is not, we have not done this here, but these things are all covered on the quiz. I can show you. Okay? So these things you should be able to show. So it's like this. I can give you a problem like this. Example. Let f of x be an even function. Even function. And then how about let g of x let g of x be an even function. Show that h of x is equal to 2 times f of x and the plus 3 times g of x. And you know what? Just g of x is an even function. So I could give you a problem like this. So this kind of problem is actually covered on test, on tomorrow's test. So you have to know how to use these definitions. So we have a function f of x, which is assumed to be even. I'm letting you know that that's even. And then g of x is an even function. And now I'm going to create another function called h of x. So what is h of x? H of x is 2 times f of x times g of x. And now your job is to find or show that this function h is an even function. Of course, we assume that f is an even function and g is an even function. We assume that. And now you have to show that h is an even function. So those kind of problems are covered. Okay, all right? Okay. Now, what I like to do is, you know what? I have not spent too much time on factoring here, so let me just save this, clear this. So let me just, I have to finalize what is covered on tomorrow's test. By the tomorrow's test will be maybe after class. We will have a regular class tomorrow, and then the class will be, the test will be, must be taken after class time. So there will be a window of time for the test. And the test, you must take the test between 11 a.m., and I'll make it about 9 p.m. There will be about a 10-hour window. Is that clear? The midterm zero, the time limit, I think, will be about 2.5 hours or so. Well, I have not written the exam yet, so I have to see. But anyway, about that time, okay? So now what I'm going to do is I'm going to now go back to this file, M0 test prep. I'm sorry that I could not do too many examples here, but these topics are covered. So the things which are covered, but I didn't spend too much time, are topics like this: factoring, example 17, 18, all the factoring skills, like monomial factoring, group factoring, trinomial factoring, and special factoring, difference of squares, sum of squares, all that is all covered. And then especially example 18, apply rational zeros theorem and factor theorem. I don't know. Have you heard of this theorem here? Do all of you remember what the factor theorem is? Factor theorem. Do you know what the factor theorem is, everybody?
Could you quickly go over it?
Yeah, factor theorem is actually it's one of the nodes. So now, so what I'm going to do is I'm going to open up a file. What is the file? A factor theorem. Where can you find this fact? A factor theorem here? Yes, the factor theorem is this. Let's go to the directory M02, and if you look at this, this is M02, and then within M02 directory, there is a file. I think this is chapter 3. And chapter 3 is factor theorem here. What is this? Zeroth polynomial. Is it section 3.3? Is it this one? Complex zeroth? I think it's section 3.3. This is M02. This is under the directory M02, section 3.3. And zero theorem here, and there we go. That's called the factor theorem. So the factor theorem is this, remainder theorem. The remainder theorem is the remainder theorem. We have a remainder theorem. And the special case of remainder theorem is called the factor theorem. So let me show you this. Okay, so remainder theorem. Let me explain to you what the theorem is. That f of x be a polynomial. First of all, this only applies to polynomial. So f of x is a polynomial. Now, when f of x is divided by x minus c, if f of x is divided by x minus c, f of c is the remainder. Now, if f of c is equal to 0, then f of x is divisible by x minus c. That's called the factor theorem. So I'm going to explain to what that means. So let's say, for example, example 1. Example 1. Now, if you try to factor example 1, there's no way to factor this using those basic techniques like monomial factoring, diagonal factoring, group factoring, and special factoring. This guy, you can try all of them. It does not apply. Cannot factor this with those kind of techniques, those basic techniques. So now the last thing we're going to apply is by factor theorem. So what is the factor theorem here? The factor theorem is this. The factor theorem is now in this case. What is this? Here, try f of 1. What is f of 1? If you try f of 1, is what? 1 and then what? Minus 6, and then plus 11, and then what? And then minus what? Minus 6. And that happens to be what? Happens to be 0. If f of 1 equals 0, is that a good thing? Yes, it is. What that means is, so if f of 1 equals 0, what that means is, this means that f of x is equal to x minus 1, and then times a polynomial. In other words, x minus 1 is a factor. So basically, here is the theorem. If f is a polynomial, if f of c is equal to 0, then x minus c is a factor. F of x is divisible by x minus c. It's the same thing as saying f of x has a factor x minus c. That's what it means. Again, f of x is divisible by x minus c means f of x has a factor x minus c. That means this is what it means. If f of 1 is 0, then that means f of x equals x minus 1 times something, means that x minus 1 is a factor. Same thing as saying f of x is divisible by x minus 1. So now the question is, how do you get this factor? How do you get this polynomial? Now, that one is easy. That one we can do this by synthetic division. 1 minus 6, and then 11, and then minus 6. And then what do you do? Divide by x minus 1. So you put 1. So 1, 1. Minus 5, that was minus 5. So 6, so 6. And then 0. With this. So now, what is the conclusion? The conclusion is this: f of x is equal to x minus 1. Now, I'm now writing the division in polynomial form, by the way. This is now x squared, and then minus 5x, and then plus 6. And then now, once we get to a quadratic, we can now factor the rest of it. So now, what is this equal to? That's x squared. So that is now equal to what? X minus 1. That's x minus 2. X minus 3. And now that's done. The only downside, the only problem with this method is, well, we tried f of 1, and then how about what happens if f of 1 is not 0? Then we cannot apply the factor theorem. So now we try 2. With number 2. Or do we try 3? What numbers do we try? But the trick is, there's so many numbers out there. And so now, here comes the rational zero theorem. The rational zero. This is the important theorem on here. So what does the rational zero theorem say? The rational zeros tells us what numbers you should try. Okay? You should try for factor theorem. Try to apply what factor theorem. So the whole point of this rational zero theorem is a list of numbers which you should try. And then if you look at the rational numbers here, and let me just make it very simple. What are numbers you should try here? You should try, in this case, according to rational zero theorem, these are the numbers you should try, and they are from here. What you should try is you have to try what? Try x is equal to, and then what? Plus or minus. In this case, we look at the number 6 here. One factor of the 6 are 1, 2, 3, 6. And then divide by over the factors of the leading coefficient, which is an. What is an? An is this guy. A0 is this guy right here, which is a constant. In this case, this is just 1. It's 1x cubed. So in this case, according to the rational zeros, what do we try for this example 1? The numbers you try are plus 1 minus 1, plus minus 2, plus minus 3, plus minus 6. There are only 8 numbers you try. So once you find one guy, then, then in this case, basically that's it. Anyway, you know what? Review your remainder theorem, chapter factor theorem, and rational zero theorem. This is section 3.3. Again, and all the files 00 and 02 and M02 under the directory M02, focus on all sections on chapter 1, 2, and 3. I'm not going to give you anything on chapter 4 or 5 or beyond, okay? Chapter 3 is what? Exponential and log, and chapter 4, and then chapter 5 is what? No. Chapter 4 and 5 is exponential log. Chapter 5 is trigonometry, so I'm not going to give you those. And then I'm not going to give you anything beyond that, okay? So focus on chapter 1, 2, and 3 under the directory M02. It's all there. Okay, you have a long day today, okay, if you want to do well in this course. So let me just save this. What I'm going to do is let me just go back here. Oh, now I think we have only a few minutes left. So what I'm going to do now, let me just clear this. So what I have is, let me go back to the file. Where's the file? So let me go back to the file here. Yeah, there we go. So I need to go back here, and what's the file? M007, 0700, this one right here, M0 test prep again. And these, we have done this. Okay, so real numbers and inequality, you should study these guys too. I will only, if I give you absolute value, linear absolute value inequality only, I'm not going to give you anything fancy. Example 16, 15, 16, 16b, these are called absolute value inequality, but they are linear absolute value inequality, only linear, 5x minus 1. I'm not going to give you anything. And then example 17, 18, factoring and factor theorem, you have to know all that. And then I was going to plan it to the example 19 as well, but let's not cover example 19 here. I'm not going to give you any graphs yet, okay? I was going to, but I'm not going to this time. And then that leaves example 12 and 13. Linear inequalities, you know what? Am I going to, should I give you on this one here? You know what? Let me just skip example 12 and 13 as well. Example 12 and 13 are called linear inequality. Sorry, not linear. They're called rational inequalities. But you know what? We have not done it. Yeah, so, you know, I'm not going to cover it. Now, sometimes, let me tell you, sometimes I give you a problem, which I told you that I would not include. But sometimes I put those on the test anyway. But instead of making regular problems, I make those as bonus problems, okay? So it will be fair to those people who know it. So again, sometimes I do give you problems which are a little bit more than what is required, and I make it a bonus question, all right? So if you just study extra, it doesn't hurt you. Okay, so again, let me just stop here. We will have a test tomorrow. The test will be after the class. So tomorrow, regular class meeting, midterm 0, after class. All right? Okay, so let me stop here. All of you have a good day, and I will meet you tomorrow. All right? Bye, everyone.
Before you go, Professor, is there practice? Are there, aside from the online materials, are there other practice questions we can use to prepare for the midterm?
You mean besides the notes?
Should we just focus on the notes? Is what I'm trying to get at.
I think it would be a good idea if you just, grab one other, maybe a pre-calculus textbook and study the earlier chapters.
All right. Thank you.
I mean, there's so much material out there. I don't think I need to provide more material. I mean, there's tons of material out there. You can find anywhere. And you can, open stacks, or you can go to any textbook, any intermediate algebra textbook, any pre-calculus textbook. They have most of the examples which I mentioned, most of the topics which I mentioned in class. But I have listed all the topics there. You can find those topics on the internet. I mean, there's so much out there. I don't think I need to give you more. You have enough.
All right, so chapters 1 through, I believe, 3, you said?
On pre-calculus, on the directory 0, yeah. But every textbook is a little bit different.
Right,
but,
I'm sorry.
But I'm not going to test you on any exponential function, log function, trig function. I'm not going to give you anything on those things, okay? And I'm not going to give you anything on ellipses or conic sections. I'm not going to give you those. So there's a lot of topics which I'm not including. I'm not going to give you any problems of sequence and series, things like that. But only the ones, here, it's mostly algebra stuff. The pre-calculus, but mostly algebra and basic geometry.
Right. So 0 through, all right. So in the online files, you said 0 through 4, I think? Or did you say up to 4?
So basically, on our class, there are files named, a file named, let's say 00 something, and then 02 something, and then the next one will be like M, you know what, I need more space here. And then M02, this is actually directory. If you go to that directory, then you will see M02 and then a section, and then a section, let's say 3.8 or something. And that means this is actually mapped to chapter 3. So under the directory M02, for tomorrow's test, study everything on chapter 1 and 2 and 3.
That's M03 as well?
M03? There is no M03.
Oh, I see. I misunderstood. Thank you.
There's no M03. The M02, that's a directory. If you open up that directory, then you'll see a bunch of files, and then they're named by sections. And for this test, you should focus on chapter 1 and chapter 2 and 3. 1 and 2 and 3. And this one, which I just opened, which one was that? All the files which I opened are within chapter 1 and 2 and 3. You know that Factor Theorem? Factor Theorem is chapter 3 also. For section 3 point, I think was section 3 point, was it section 3.3 or 3.4? It's all there.
Thank you.
Okay? Okay, good. Very good. Anyone else have any questions?
I had just a general question. How much more difficult is Calculus 2 compared to Calculus 1?
Calculus 2, well, you know what, just like in Calculus 1, in order to succeed Calculus 1, I think the important thing is that you need to have a strong base, which is pre-calculus and algebra. Now, in order to do well in Calculus 2, you should have a strong base in Calc 1. So if you have a very strong base in Calc 1, then Calc 2, they do cover new topics, but the difficulty is, I think, you know what, I think it's very manageable. That's what I can say. But Calculus 2 structure is a little bit different. They cover a lot of different topics. In other words, Calculus 2 is like between Calc 1 and Calc 3. When you look at Calc 1 and Calc 3, the topics are very uniform. But then Calculus 2 is like a bunch of little things here and there. It's like it's a different form. Not all contents are unified. It's a bit of many things. But Calculus 1 is very uniform. The whole thing is like one unit. It goes they're all connected very closely. But Calc 2, you can do it. But you need to have a strong base in Calc 1. So if you don't do well in Calc 1, or you don't know it, it's not ready, then you can't do Calc 2.
Okay.
So math, that's how it is. Just like this course, you need to have a very strong base in algebra and pre-calculus. Then this course, I think it should be okay. That's why I'm stressing so much on this algebra and pre-calculus. Because you need to have a very strong base here. So one of the major reasons why students cannot do well in Calc 1 is because their algebra is not ready. Or very weak. And that's what I'm trying to get at.
Okay, thank you.
Okay, very good. Okay, bye.